from Taipei. Let's talk about something on graphs, but in a slightly different form, right?
Right.
Please.
Okay. Thank you. Thanks for giving me a chance to talk to Sangil and Semyon for inviting me. Right. So I've given this talk on this project a few times before, but it was always to more of a tropical or algebraic geometry audience. I was informed for today I should try to talk more about graph theory, so I've tried to move things around a bit, and hopefully this is I guess I maybe in some ways I see myself as a graph theorist, but there's a lot of parts of graph theory I'm not very familiar with, and I'll try to talk about a few of those things today. Right, and so at the beginning too, this project is something I worked on with Omid Amini and Luca Gierzak, who are both in France currently. Okay, great. So for this problem, I think I want to start with the graph of, today I want to start with the graph isomorphism problem, which is, I guess, a pretty commonly easy to understand problem that, and with a long history in theoretical computer science and discrete math. So the problem is, if we're given two graphs, finite graphs, can we decide if they're isomorphic or not? Can we either, and perhaps given isomorphism if they are, so here I have like two cases of this problem. So say for the top one, maybe by show of hands, who thinks these are isomorphic graphs? Okay, it's not very many. Okay, maybe I'll give 10 seconds. I'll ask for both pairs of graphs. And I don't know if should I give a hint? I guess this is later in the day. I don't know if that means there's more likely I should give a hint or less reason to give one. Okay, I guess I'm happy with the lack of answers. Okay, so I guess for the first pair, by show of hands, who says they are isomorphic? Okay, great. And for the second pair, by show of hands, who says they are isomorphic? Okay, I think as a group you are kind of correct. So in fact, the first pair is isomorphic and the second pair is not. Yes, good job. I think I counted three people who were brave enough. So in the first case, this pair, both graphs are isomorphic to the Peterson graph, actually. And I guess in the Peterson graph in particular, it's something that comes up in a lot of areas, but I have this kind of pet peeve that it seems like it's always drawn in this bottom way, but I think these top two ways are also very symmetric, nice presentations for like drawings for this graph. So I guess this is my way of trying to advertise this more. And and all three of these in fact have kind of tropical interpretations. In fact, there's like tropical moduli spaces where each of the three interpretations like has a sort of moduli meaning as well. But that's not really the topic for today. For the second pair, they're not isomorphic, and one way to check this is by counting the number of spanning trees. So this is something there's a lot of spanning trees, so it's hard to count them one by one, but you could use the matrix tree theorem to do this more efficiently, and you can see that there's different numbers of spanning trees, so they can't be isomorphic. Right, so this, I guess this is a hard problem, even for fairly small cases, I suppose. It gets hard quickly with the size of the graphs. But it's interesting within theoretical computer science because currently the sort of the complexity class is still open. It seems to be believed that it's in fact it's NP intermediate complexity, which means it's outside of polynomial time, but also not in NP complete problems. So so it lives somewhere like this, and in particular this also implies like P is not equal to NP, which is also, I guess, well known to be open. I guess there's also, and this is all material I'm not that familiar with. I just tried looking stuff up briefly to prepare these slides. You can look at very similar sounding problems like subgraph isomorphism. So if you ask for one graph G, does it contain a second graph H as a subgraph? So this is NP complete. And one way to see this is it contains well-known problems like the question of whether a graph has a Hamiltonian cycle. So somehow changing its subgraphs makes it harder in this complexity sense. And currently the best known running time for an algorithm for graph isomorphism is here, so n to the power of log n, for that constant b is something positive. And right, so although it's not known what the complexity is for arbitrary graphs, and it's believed to be not polynomial, this problem is polynomial for certain classes of graphs. So for certain special classes, we only look at graphs of bounded degree. It's polynomial time. We can look at graphs with bounded embedding genus. So that can be bounded in a surface of bounded genus, embedded in a surface of bounded genus, and then also look at these conditions like excluded minors. Right, so even though all of these are known to have polynomial time algorithms, a lot of these algorithms are not actually very efficient in practice, I guess in terms of having implementations that finish quickly. So, right, and yeah, for the bounded degree thing, I think I'll come back to have a comment about that later in a minute. But right, so in terms of how you would typically approach the graph isomorphism problem in practice. So the currently the software implementations to solve graph isomorphism that seem to do the best in practice all use this approach, which I think if I understand correctly is not one of these polynomial time, or which is different than like the Babaya's method for the asymptotic complexity. So roughly what you do is you try to label the vertices in such a way, in a canonical way. So for both graphs G and H, you apply the same labeling algorithm, and then you check if whether the labels match. Or you only need to test the matching labels once you do that. And one way of assigning labels like this is doing this kind of coloring refinement process. So it seems that you color and start with one vertex arbitrarily, and then you look at its neighbors, and if other graphs have the same number of color neighbors, then you assign the same color to those. So somehow you iteratively assign colors throughout your graph. And I guess here it does start with initial choice. I didn't read enough to find out how that gets resolved in the end, because you want something that is independent of the choice, I suppose. Okay, so this is this figure was taken from some slides of Brendan McKay, who's also responsible for Nati, one of these implementations for graph isomorphism.
In the second
Yes.
graph, why do the vertices get yellow color? The number of white neighbors they have are different.
Right. So I think here we consider the white neighbors not as part of the coloring. Only the green neighbor is being colored. Yeah, that's my understanding.
On the first graph, right? So you color, but it's red because in the first graph you only have one green neighbor. Oh, I see. Now I see where you were pointing. Okay. Sorry.
Yeah. Also, I guess probably I'm definitely not an expert about this though, but hopefully this at least illustrates the idea of what types of what typically gets used for practical graph isomorphism approach. And right, and I think I guess in these sorry I pressed the wrong thing. And I think the current implementations, they seem to work reasonably well for graphs maybe up to 1 million vertices, I think, and within I think a few hours, like within a day. This was also from what I learned from the slides. Okay, right. And I also, something kind of funny I learned at some point, that graph isomorphism was such a popular problem within theoretical computer science that people decided to write this paper called label it the graph isomorphism disease back in the 70s. So I guess nowadays things have moved on, so now graph isomorphism is no longer so popular because I guess there are other things that have taken the attention of the computer science community, which perhaps could also be called diseases, arguably. Right. Okay. So now the main content of what I want to introduce today is this graph structure called the Weierstrass weights, which is a way of assigning positive integers and non-negative integers to the vertices of a graph. And so this is just one example. I guess in some of the later examples, if a vertex is assigned 0, I might just leave it blank, and so 0 should be assumed. And then here I have labels go from 0 to 4 in this particular case, and I guess one basic property I mentioned at the beginning is the labels on the graphs you get from these weights are bounded above by the genus, where by genus I don't mean the embedding genus, I mean like the number, you could say the number of independent cycles on the graph, or the number of edges you have to remove to obtain a spanning tree. And a direct formula is here, you take number of edges minus number of vertices plus 1. And and one reason I like calling this genus is that's the tropical terminology, because it serves as an analog for the genus of an algebraic curve. Okay, so here's just one example of what the Weierstrass weights look like on one graph. And so here's another example. So for one pair of graphs I showed at the beginning, the non-isomorphic pair, if you compute the Weierstrass weights on each side, you'll see that it's like a different multi-set of weights. So one graph has a vertex with weight 0, and the other graph does not. So this provides it. If you're able to compute these weights, this would also give you a test that they're not isomorphic. And this works because these weight assignments are graph isomorphism invariant. You're not making any arbitrary choices when you obtain these weights. And it's a kind of vague intuition that I believe is true about these weights is they tell you something about some sort of mix of local and global structure of a graph. So one argument for why they're in some sense global is, so if you take two graphs, you can form their twosome. If you have two graphs and pick two vertices on each graph, you can join them by a pair of parallel edges, but you can join them in two different ways. You could add a twist in the middle or not. So here I have an example of two of these graphs where one is, say, twisted and one is not. I guess this side stays the same and the left side gets flipped upside down. And so here you can kind of see that a lot of the weights end up changing despite sort of the graph, the structure inside G and inside H stays the same. Okay, so maybe this is still a fairly small example, but I guess that's showing the sort of the global nature of these numbers, and then also I think for the local argument, I'll come back to that later when I explain how they're computed. Why, in some sense, they are still local, not completely global. Okay, and maybe any questions before I go on? So then I'll give some terminology and then actually give a definition for how to get these numbers.
So is it easy to calculate the Weierstrass weights, or?
Yes, it is polynomial time at least. And I'll say a bit more, I guess. And so I did, I guess to get these figures, I did implement, like on my website, there's a place you can just enter in a graph by, say, an adjacency matrix and see these Weierstrass weights. It's not an efficient implementation, I'm pretty sure. So it is very slow once you go past like maybe 50 vertices, but I guess maybe one goal I have is to do a better implementation of this. So, so to first give some terminology before going on to the definition. So within tropical geometry, so we can think about graphs as tropical curves, and we call if we assign if we assign integer values to the vertices of a graph, we can call this a divisor or chip configuration. So maybe when we talk about chip configurations, we might be thinking of just the positive case or non-negative case, but divisors, in general, we allow negative values as well. Yeah, and then we would just write this with as a formal sum and integer times the vertex added together. We say the degree of the divisors, we just add up their coefficients and forget the vertices. And then one special divisor that's important for us, important in tropical geometry, is this canonical divisor where the coefficient on each vertex is its valence minus 2. And the valence, by valence I mean what's usually referred to as degree in graph theory, but we're using degree for this other thing. So yeah, I mean, it's a bit unfortunate. But so here's two examples of showing the canonical divisor on two graphs. So for a tree, the leaves always have negative ones, and the interior vertices will be non-negative. And then, so for a tree, if you add up all of the coefficients of the canonical divisor, you'll get -2, because the tree is genus 0. And then in the second case, this house graph, you see it has degree 2, and that also sort of agrees with this general genus formula. This is, since it's a genus 2 graph.
So genus was number of vertices minus number of edges plus.
It's edges minus vertices,
Oh,
and then
minus
plus 1.
vertices plus number of components.
Oh yeah, I am assuming connected graphs. Yeah. So, genus. I don't think I'll need disconnected graphs anyway. And then, yeah, another way of, I guess, defining this in terms of the topology of the graph is, so as a topological space, this is 1 minus the genus, gives the Euler characteristic. Right, so to compute these Weierstrass weights on a graph, what we do is we choose a vertex, and then we compute what's called the reduced divisor at that vertex, and then we just subtract a fixed amount from that, from the coefficient in this reduced divisor. So in the next slide, I'll explain how to get the reduced divisor, but suppose if we start with this vertex and we do some process, and this is our reduced divisor, the coefficient at our chosen vertex is 10 here, and then the genus for this graph is 7. So then we just subtract 10 minus 6, and that gives us 4. So that's our the value. And I guess this all seems very arbitrary as it's defined here, but it comes from algebraic geometry. That's why the definition is the way it is.
Sorry, can you remind me what was reduced in the reduced divisor?
So this is just terminology for, yeah, I guess this terminology comes from the like tropical curve field, but yeah, I guess the intuition for why it's reduced is it, so given a divisor or a chip configuration, you're allowed to move the chips around according to certain rules called like linear equivalence or chip firing, and then within some equivalence class, the reduced divisor is the one where all the chips move as close as possible to the chosen vertex. That's the intuition.
And for these weights, you use the canonical, I don't know how you call it.
Oh, yes, yeah.
Canonical-
That's right, yeah, starting from the canonical divisor. Yeah, I should have said that here, yeah. So we always start with the canonical divisor, and then compute the reduced divisor at our chosen vertex.
So the reduced divisor is the one that after lots of chip firing, you want to minimize the number of chips at certain vertex, or?
Right. You want to maximize the chips at your chosen vertex and minimize the amount of chips elsewhere, and also minimize their distance. You want to get, like, for the chips away from your chosen vertex, you want to get those chips as close as possible.
Ah, I see. And then you want to look at the V coefficient of the reduced divisor.
Yes.
Of the canonical
Right.
divisor.
Yes.
Yeah.
Yeah. Another way to characterize the reduced divisors, you can define some energy function on the set of divisors where the energy function depends on your chosen vertex, and the reduced divisor will minimize this energy. Okay, so now to say, right, so you get the Weierstrass weights from taking the reduced divisor, and then how do you get the reduced divisor? So the process of obtaining the reduced divisor is, or the standard way of describing it is you go through what's known as stars burning algorithm. So here I've like shown all the steps for one specific case, and here you read the rows like horizontally and then down. So at the chosen vertex, what we want to think about is we set this chosen vertex on fire, and the fire spreads across the edges, but the other chips are going to stop the fire. And so if you have this, say on this chip, there's a single fire coming on one edge, and there's one chip there so it can stop it. And so in this case, like 3 of the edges are on fire, but it's stopped and it can't go any farther. So at this point when the fire is stopped, what you can do is you move all of the chips that are bordering an edge on fire, you move that chip inwards across the edge. So after we do this one step, we get this configuration now. There are now 4 chips at our chosen vertex, and there are no chips here, and then beyond that there's 1 chip. And yeah, and I guess for a lot of my examples, I'm
So initially the number of chips at the vertex is degree minus 2. Right?
yeah, that's right, that's
Yeah,
right.
so-
Yeah. So we're starting with the canonical divisor. I think most of my examples on these slides will be cubic graphs, so that has the convenience that the canonical divisor just has degree 1 everywhere, or just has one chip everywhere.
One chip everywhere.
Yeah. Right. So after sort of one iteration on this stars burning out, we get this configuration, but then we repeat. So now we set this on fire again. Now the fire spreads along 2 edges in every direction, but then it stops. So now we move those chips inwards, and we fire those chips inwards, and we get this configuration. And then we now repeat again here, and then fire them inwards. And now we have 10 chips in the middle, and then 2 chips are left over on this corner. So now from here, if we set this chosen vertex on fire, so the fire will spread across here. There's no chips to block its progress until here. But now what happens is at each of these vertices there's 1 chip, but there's 2 incoming edges that are on fire, and so the fire can't be blocked because there aren't enough chips. So if there's 2 fires here, we need at least 2 chips to stop the fire, but there's not enough chips, so I guess they get overwhelmed by the fire, and then the fire just spreads beyond that. Right. So what happens in this case, in this configuration, when we start the fire and allow it to spread, it spreads over the whole graph, like every edge. Every edge and every vertex becomes on fire, and then we finish. So that tells us we're finished finding the reduced divisor. So that tells us this configuration is reduced. Right, so that's our coefficient is 10, and we subtract g minus 1 to get 4. Any questions here?
In the second row,
Yeah.
we did this chip firing at 3 vertices, right? The neighbors of this.
Right, to get from here to here.
No, from there to the next one, right? So then, I'm wondering what. So the middle one has 4 chips at the moment, right?
Right.
And then, don't you distribute 4, like one of them to neighbors?
Oh, outwards?
Outwards?
So here, often when chip firing is first introduced,
Yeah.
it's introduced where you fire at one vertex and you spread the chips outwards.
Right.
But I guess what I'm trying to illustrate here is kind of opposite effect. So if you, right. So if you started with this and then you fired this vertex and spread the chip outwards, it would kind of go backwards to this
Yeah.
configuration.
But I thought you're firing chip towards the neighbors of this center, right? There are 3 vertices and you're collecting chips from neighbors, right?
Right.
And then you do it 3 times, so that I thought 4 becomes 1, but
Yeah. I guess the order I'm illustrating it here, it's kind of the opposite direction than the usual direction for chip firing. But the way chip firing, it's it defines a group structure, so both orders are allowed. And so if you think about like firing, so instead of So yeah, you can think about going from here to here as doing like a negative chip firing operation at this vertex, or you could alternatively think about I'm going to fire every other vertex except for this one. And if I so if if all of these other vertices I like send one chip outwards in each direction, each neighbor, that will add up to sort of this process in the
So sorry, what is exactly the standard chip firing operation? Because I mean, your example gives some idea, but for instance, if you have six chips on the vertex of degree 3, what happens if you fire that vertex?
So the standard chip firing is you would send exactly one chip on every edge that's incident to you. Yeah. Yeah. So yeah, going from here to here would be like the usual way that a chip firing move is introduced. So yeah, but in this process, like instead of sending chips outwards, we end up sending chips inwards towards our chip inwards.
Could you just repeat when does this process end?
Right. So in these cases, when you spread the fire, it stops. It stops where it only a strict subset of the graph is on fire. But then in this case, in this last row, when we start burning the graph, we end up with the whole graph on fire rather than a strict subset on fire.
And that was because every chip can only stop the fire from one edge.
Yes.
Yeah.
Do we take one chip for each time or take everything? So for instance, in the third process,
Oh
we
yeah.
actually do 2 times, or is it only 1 time and take 2?
Right. So here I think.
If it's 2, 3, then
Yeah, I guess to be more precise, I would have to say I'm doing this operation twice here.
twice as.
Yeah, because one operation you would only send in one chip from each of these neighbors rather than 2. Yeah. So I guess I have one second example to try to illustrate. So now if instead of the first vertex we chose, if we chose one of its neighbors, and we do this process, we'll see that I guess the first step looks the same. The second step, we end up with sort of this half of the graph being burned, and so these 4 vertices, these 4 chips end up moving in this direction, and then so in this case it's a bit less symmetric, but I guess after in the 4th iteration still, after this 4th iteration, the whole graph ends up on fire, and so then we end here with a reduced divisor. Right. So and in particular, something different we see here is in this reduced divisor, we have a coefficient of 6, and after subtracting g minus 1, we get 0. So here the Weierstrass weight is 0, as opposed to being positive before. Okay. Maybe any other questions based on this?
Why is it called Weierstrass?
Okay. I think my almost second to last slide will explain this, but the terminology comes from algebraic curves. I guess. Yeah, I guess Weierstrass. I guess his name comes up a lot in analysis, but also he studied algebraic curves. I guess back when algebraic curves meant you studied them over the complex numbers, so it wasn't as separate from analysis, I suppose.
So in this example,
Yeah.
the second last drawing, I guess it is wrong because there should be one chip on the right side, isn't it?
On the right side,
The bottom chip go to there, isn't it? Wrong or am I?
sorry, this one or
Yeah. So there's in the third last drawing.
this one?
Yeah. So the bottom vertex is say degree 1 in the red graph.
Right.
So these should be moved to the right upper side, or am I confused?
Keep here, move this
Yeah.
way. So that would be like in this step. So the chip would move if the fire spreading process stopped here, but it's not at this point the fire still continues to spread. So that's like if you only look at this part of the graph, it looks like the fire was stopped. So here was stopped and here was stopped, but the problem is over here and here the fire was not stopped sufficiently. So to decide that the fire was stopped, we have to look at the whole graph.
Ah, I see.
So yeah, because of these positions, the fire ends up spreading farther and it goes down and then ends up filling the whole graph. But yeah, so good point. Yeah. So to check that the fire was stopped and we move the chips, we need to check at every boundary point that the fire was actually stopped. Okay, yeah, so I guess now you have all information you need to compute the Weierstrass weights on any graph, any finite graph. With sufficiently large sheets of paper. Okay, now, so to say a bit about what the running time is for this process. So just to compute this Weierstrass weight at just one single vertex, so basically the fire spreading part of this process, we're running breadth first search. So like this running time is number of vertices plus edges. And then once we see where the fire has been stopped, if it stops on a proper subgraph, then we do this chip firing, and then we go back and spread the fire again. So then this middle part of the algorithm where we keep iterating through this process, and the number of times we need to iterate is bounded by the diameter of the graph. And so this, and so for this diameter thing, so basically this running time will be the time of breadth first search times the diameter of your graph. In the worst case, the diameter could be on the order of the number of vertices. So we get this worst case time. And then for on average though, if we say take a random graph on a fixed number of vertices, maybe the diameter I think should be more like log of n, log of number of vertices. So we get something a bit faster. And right, and this was just for one vertex though, and we need to do this for every vertex. So then we could multiply this all by the number of vertices. But I think instead of doing this from the start from every vertex, I think you, I think practically you do gain, it is more efficient to just start, if you already reduce the divisor at one vertex, it's much quicker to then compute the reduced divisor at a neighboring vertex rather than starting from scratch. I didn't check if it's actually asymptotically faster, but I'm pretty sure it should be faster in practice. But yeah, I guess that's maybe worth exploring, like writing down the details of. Okay, but yeah, in any case, it is a polynomial time thing to calculate all the Weierstrass weights. Okay, right, now to go on to this question of can we give any like global bounds or constraints on what numbers we get when we compute these Weierstrass weights. So it turns out, I guess a basic property is the one I mentioned before. The Weierstrass weight at a given vertex is always bounded above by g minus 1. Oh yeah, so and the g minus 1 is a strict upper bound. It is obtained for some graphs. In particular, it's obtained on any graph where we can take a quotient of the graph that's a tree, or if we take like a ramified double cover of a tree, which I didn't draw a picture of, but I can, I guess, draw a picture later if you're curious. And but beyond this, it turns out I don't know if any really nice bounds on just looking at these weights of the vertices. But it turns out I can say a lot more if I consider a kind of related idea. So one property of these weights is that if we subdivide the graph, so if we take each edge and we subdivide it into, say, m sub-edges, like in this process, I think I chose m equals 7, and we do this for the same way for every edge, then all the weights we had initially will stay unchanged, because I guess the chip firing or the Dars burning algorithm doesn't really care how long the edges are. It'll just repeat the same thing more times the longer the edges get. And right, but you end up getting new information when you do the subdivision. So once you do the subdivision, you have more vertices in the interior of the edge, and these might have positive weights as well. So it turns out that this is well defined in a sense that you can sort of take a limit where you allow all the vertices in the interior of an edge, and they still have well-defined weights in this sense. So we call this the associated metric graph, where we think of each edge as just a unit interval. So it's some continuous space with a topology and a metric induced by this, like the interval in the shortest path metric. So on these associated topological spaces, we also have this notion of like this Weierstrass number or assignment. And yeah, I guess the terminology, I'm about to sort of give a different definition of the weights than before. So here I defined a weight for an individual vertex. And then it turns out when you take this limit, this continuous limit, you might have, now that these red points won't just be discrete points, you could have entire intervals that are entirely colored red. Okay, so
Does the
right.
Western weights non-negative? So in that example, it's non-negative.
Yes, yeah, exactly. So this is also this follows first by some like important results about tropical curves, I guess, from Baker and Areen. And yeah. So yeah, maybe I should mention, given this picture, like when you do the subdivision process, and then you count how many red points you get, the number of red points you get can grow to infinity. But then if you think about it as a topological space, and you've got these connected components that are colored red, it turns out there's only finitely many connected components in the end. Okay, so this was, I guess, one of these main results in my paper with Omid and Luca. So we can show there's finitely many of these connecting components in the Weierstrass locus on a metric graph. And then we can also give a weight, the formula for a weight for every connected component. And so this will look different than the one I defined for a single point, but I put it on the next slide. But using these, using this formula for the weight, it turns out the total weight on any metric graph of genus G is going to be exactly g squared minus 1. And every connected component also has a positive weight. So in particular, that shows that the number of components has to be bounded above by g squared minus 1 as well. So in this case, we had a genus 7 example graph. So there's at most 49 components, like red components, if we take this continuous limit. I still haven't actually computed, in this case, how many components there are in the end. I only subdivided up to here. So I think this is part of the problem with my implementation not being very efficient.
So what do you mean by components? You mean look at the in the limit, right?
Right.
So when you have 0, then you delete or
So I think it might not be. I don't think there's a good way to actually define common components just from taking this limit as I described, of just subdividing. But it turns out you can. What I showed on the previous slide about taking reduced divisors, that's something that's well defined on a metric graph as well. And so that allows you to pick any point along the interior edge. You could run this reduced divisor algorithm to compute a reduced divisor, and you take that coefficient minus, and then subtract g minus 1. And you color it red if that's positive, and 0 if it's 0 after subtracting.
So this is component of metric graph, or is it component of
Yes.
some space, topological space or something?
Right, components on a metric graph. Yeah. So this, for the metric graph, like using this tropical geometry perspective, every graph, it's naturally thought of as a metric graph. And there's also this associated structure called the Jacobian of that graph, or the tropical Jacobian, which is a g-dimensional space. Like it's a g-dimensional polyhedral complex. And then a lot of these, so these facts about the Weierstrass weights, you could also define, you could sort of, describe in relation to the Jacobian as well. And I think potentially like using the Jacobian, you could maybe get other interesting graph invariants that are worth exploring. But I guess for today I didn't really prepare anything about the Jacobian specifically. So
in our whole discussion, we only consider like, graph with cycles. We also care about trees. So I mean, genus is 0. So like weight is negative and everything.
Oh.
So,
like, is it interesting to consider genus 0?
yeah.
In
So
this case?
do we?
I think the answer is no. Yeah, I might need to double check. But yeah, I think we need positive genus to get anything interesting. Yeah, and I guess the formula doesn't really make sense for genus. Yeah. I think for this result, I do need to say positive genus. Yeah. But yeah, I think graph isomorphism is easy on trees.
Yeah.
For what it is. to go back through, if that's our motivation here. Yeah. Right. So in this result, the weight we define takes this form. So this G is the ambient graph, the genus of the ambient graph. Here we also use the genus of the connected component. So let's say we can define that using the Euler characteristic, or the count vertices and edges of that subgraph. And then finally this other more complicated term, it's a summation over outgoing directions of this connected component, and for each of these outgoing directions we take some slope, and I'll try to just illustrate that with an example. So so this is some number that's attached to this process of going from the canonical divisor to the reduced divisor, like I illustrated on the previous slide. So in this process there are like many intermediate steps, and in many of these steps I move chips across edges. So if every time I moved a chip across an edge, I recorded that down, and and then I want to record the net number of chips that cross an edge along with their direction. So if I recorded that down in this case, I would end up with these numbers. So many of these just have a single chip cross them, but for two edges, I had 2 chips cross the edge. And so the numbers I want here are exactly these numbers showing up. So yeah, in this case, say if my connected component A is just this vertex, there's 3 outgoing directions corresponding to these 3 edges, and then the slopes would be 2, 2, 1 here. Right, so I think it would be possible to, if we plug in, so the genus of a single point is 0, and then we do, so 8 times minus 1, and then subtract these. If we plug in 2, 2, and 1 here, I think we should still get 4. But I also didn't prepare, and yeah, maybe if there's time at the end, I can go back and check if that's true or not. But yeah, this was, I guess, one of the main motivations for this result, though, is because an analogous thing is true for algebraic curves. Like the place where these Weierstrass points were initially studied, there's some fact that the total weight of the Weierstrass points only depends on the genus of the curve. Okay, right, yeah. So I guess this is then. So to say just a little bit about where the motivation for this definition came from, it's from tropical geometry. Okay, and maybe I should. Yeah, sorry. I think I want to start with this slide. So in tropical geometry, one of the main things people care about are these algebraic curves. So curves that, so these are spaces. If you start with, say projective space, and then you impose polynomial conditions until their solution set is only one-dimensional. But if it's if we work over complex numbers that are nice algebraically, this one complex dimension looks like a surface. So here I've sketched out a cartoons of 3 algebraic curves, right. So instead of only thinking about them with some fixed embedding in a projective space, algebraic geometers often care about like their isomorphism type. So you can define an isomorphism independent of their embedding, and so one way of studying all possible curves up to isomorphism is putting them together in this moduli space. So there's a natural notion of two algebraic curves being close nearby to each other, and right. So if I pick 3 curves that are non-isomorphic, these would correspond to 3 different points in their moduli space. And algebraic curves also have a genus. So the genus here in this case is, we can think of as like how many handles you have to attach to a sphere to get something topologically equivalent to your surface. So in this case, these are all genus 2 algebraic curves. Right, it turns out if we consider all genus 2 curves, genus 2 algebraic curves, there's a 3-dimensional family of them, considering them up to isomorphism. In general, for genus G, the dimension of the space is 3G minus 3. Right, so we have this moduli space, and there are many questions about these algebraic curves that are still open, even though mathematicians have been studying them for a long time. So things like what are all the homology groups? I'm pretty sure like for this moduli space, and there's also some standard compactifications that people care a lot about as well. It's not known what all the homology groups are. It is known, I think, asymptotically what the Euler characteristics are, and they grow very large, which tells us there have to be like lots of non-zero homology groups, and yet still the known non-zero homology groups is very, very small compared to that number. So a big open question in algebraic geometry is how can we understand this moduli space of curves better? So one approach to trying to understand this moduli space of curves is to attach extra structure that sort of comes canonically, that these algebraic curves are canonically equipped with, and Weierstrass points are one example of this. So it turns out in general, if you take a genus G algebraic curve, there's always going to be finitely many of these Weierstrass points, but in the generic case, it'll be G cubed minus G points, Weierstrass points on an algebraic curve.
So
and
what's Weierstrass points?
Right. Yeah, so for an algebraic curve, the number of Weierstrass points is G cubed minus G. And then for a tropical curve or graph, it's, I guess it's, say, bounded by G squared minus 1 if we count with multiplicities correctly. So it turns out, this bound doesn't really work if we're only looking at the vertices on a combinatorial graph, because if we add up the weights on the vertices, they might actually be attached to the same connected component. And when they're in the same connected component, we're not supposed to add them together. So I guess there's maybe with the big asterisks here, we can think there's kind of a similar bound of G squared minus 1. Right. I guess going back to, Weierstrass lived in the 1800s, so this is considered fairly classical algebraic geometry, and to the point that most people studying algebraic geometry today never learned what the definition of a Weierstrass point is. So it's kind of old-fashioned, but I guess tropical geometry is new, so you can go back and dig up really old stuff and try to do it tropically. Right, and there have been some examples of using tropical geometry to prove new results in algebraic geometry, or reprove important results in algebraic geometry. And so far, I don't know if any that actually use Weierstrass points explicitly, but that's, I guess, part of the motivation in my head. But so for the same way we can, but now the same way we can think about algebraic curves as living inside some moduli space and we can move them continuously, we can think of graphs as the same way. So if we look at metric graphs of fixed genus, for each edge we can like slightly increase or decrease the length of the edge. And that length matters because we're recording the metric. And so we can think of this as it's living above some moduli space that tracks the changes. And so potentially a way to think about graph theory is think about all our graphs living inside a moduli space and so moving around. So yeah, if we move around in this moduli space, it's like we're doing small local changes to our graph. And right, so and perhaps like knowing something about how the Weierstrass points move around on these graphs as we move our graph could help us learn about some important underlying structure of the graphs in a way that wouldn't be known about before. And yeah, so maybe to go back just to the graph isomorphism really briefly before ending. So I guess I want to propose this question of what can we use Weierstrass points to help us on the graph isomorphism problem? I would guess that it probably doesn't help in the worst case, looking at arbitrary graphs, but potentially it could in some special cases, or just as a, maybe there's certain graphs where computing the Weierstrass points speeds up the process, even if it doesn't speed it up asymptotically. And yeah, so I think one example of why it might not help very much is, I think the way I understand it, a big, like one particular case that's particularly hard for graph isomorphism is taking two highly symmetric graphs. And so if you take two graphs that are vertex transitive and you calculate their Weierstrass weights, the Weierstrass weight will be the same on every vertex by the vertex transitivity. So, so it seems that in many cases you would take two non-isomorphic graphs that are vertex transitive and you take all the Weierstrass weights and they'll all be the same, and so you don't get any useful information out of that. So I think there are some big classes where it seems fairly certain that Weierstrass weights don't help at all, but perhaps outside of that you still get useful information. And then this last bullet point, I didn't actually say anything about what the Jacobian is, but there is some extra structure called the Jacobian that's attached to a graph that comes from tropical geometry, and I think perhaps this could be useful in some ways for understanding graphs as well. Okay, so thanks for listening.
Thank you. Any questions?
For the, say, directed graphs or hypergraphs, can we do similar approach for distinguishing?
I think these Jacobians and like this, I think this trip firing structure has been studied in both of those cases. I think to me at least, it feels a bit like the directed graphs are a bit less natural in this approach. I think for, maybe hypergraphs or higher dimensional simplicial complexes, there is more hope of being a useful analog with the algebraic geometry. But I think even despite this, it seems to be pretty poorly understood currently. By me in particular, and also by the general tropical geometry community. But I could. I guess I didn't actually plug it in. There's some issues with that. I guess that,
Is there any so this the classical graph isomorphism algorithm, one of the algorithms is like this color refinement, right? So you do
right.
I forgot this WL algorithm. I
right,
can never pronounce that name. There's WL algorithm of certain step, right?
Right.
Gives you some invariant isomorphic graphs. If you have two graphs with WL isomorphic, if you have two isomorphic, non-isomorphic but WL invariant could be equal. Can they have the same Weierstrass number, or could there be examples where you can distinguish graphs but they cannot distinguish graphs with the?
Yeah, I'm pretty sure I guess I didn't look at this recently enough and put it in the slides, but I do remember looking at this at some point, and I think for the simple cases of like two graphs that look the same for this Weisfelder-Lemon approach, like they would have different Weierstrass weights. Like I think the Weierstrass weight information does give like it is more able to distinguish graphs. But yeah, I guess is there like a standard small example for this case of
With CFI graphs, I guess.
Okay.
I forgot the name. Kai Furedi Innerman. CFI is the standard.
Okay.
notation. I mean, there's no simple construction. It's.
I see. Okay. Yeah. I don't think I checked on that fam. I think what I remember was like a very simple example. So maybe it was not. Maybe it was like a simpler like.
Did you check for Weisfelder-Lemon in general, or just the color refinement? Like, is it the coloring of the vertices or coloring of tuples of vertices?
Oh, I think it was just vertices. Yeah. I think just vertices was this one I looked at. Yeah, so maybe I was looking at something simpler. Yeah. But yeah, if these graphs, if it's easy to like obtain their adjacency matrices, I think it should be possible to like check. I mean, yeah.
It can be computed.
Okay,
It's not
okay,
the
yeah.
easiest description ever.
Okay, yeah. Do you think like Claude can just output some adjacency matrices? Okay. So it'll be quick to check.
Any other questions? If not, let's thank the speaker.